Great. So today we're very happy to have Albion Lawrence all the way from Brandeis University, who's going to be telling us about the microscopic origin of the entropy of black holes. So Albion, please take it away.
Thanks. It's a real pleasure always to be back in Chicago. I'm going to started learning to think about black holes. As you'll see today, I'm still learning. So I'm going to talk about a couple of papers I wrote with Vijay Balasubramanian at UPenn, Javier Magan, who just took up a faculty job, was at UPenn and just took up a faculty job at in Bariloche, and our postdoc Martin Saucieda, who arrived at Brandeis this year, and I'll just mention that he's extremely good and worth talking to if you ever get the chance. Okay, so let's see.
I have to click on it.
Oh, this one is recorded. Got it. Okay, good. Something like that. Reading. Nor is this. Oh, sorry. I guess he's.
There's no work.
Okay, thanks. So just by way of outline, I'll start with some introduction. Much of this will be boilerplate, but I just want to, I never don't always know who the audience is. And at the end, I'll give a little. At the end of the introduction, I'll give a little executive summary of what we think we've done. And then I will launch in. I'll start by talking about just some a family of asymptotically ADS sort of two-sided black hole geometries, including the interior. And then I'll talk about computations, or at least an estimation of the size of quantum overlap between these interior geometries using Euclidean wormhole techniques. And I'll then argue that this, because of these quantum overlaps, we can show that the black hole Hilbert space is a much lower dimension than you might have naively thought. And that's the core of it. And then at the end, I'll talk a little bit about extending this calculation to asymptotically Minkowski black holes. We're going to rely mostly on the ADS geometry because at least I have a slightly better conceptual handle on what we're doing there. If it's a crutch that we can hopefully throw away eventually. And then I'll conclude partly by recapping. Instead of maybe doing an introduction. So this thing goes at various speeds. Please ask questions. I'll get to this last point. It's not the end of the world. Okay. So first, this is the review part. This first slide is probably not a surprise to too many, but we're going after an old puzzle and a new one. I'll talk about the classic old one, and that's the presence of the fact that the black holes have an associated entropy, which satisfies the first and second law. Behaves certainly thermodynamically, as Bekenstein-Hawking pointed out. The change in the mass energy is related to the change in the area. Hawking pointed out there's an associated temperature related to the surface gravity kappa. And therefore you can think of, you would naturally associate dA with ds like so. And similarly, Gibbons and Hawking computed using Euclidean quantum argued that if you compute the free energy by computing the Euclidean Einstein action for a Euclidean black hole with this asymptotic geometry, you can compute the area as a derivative of the free energy, and you get A over 4G Newton. So that's all very tantalizing, and so far it's all very thermodynamic. And so you might then sensibly ask if there's a statistical origin where the dimension of the black hole in some sense is e to the s. So if you're a string theorist like me, and I think I'm among friends here, the answer is, of course, yes. For example, Stromer, and Vafa looked at a class of supersymmetric black holes and used supersymmetry plus some non-renormalization for BPS black holes to count string and d-brane states and argue that this gave you the entropy of the black hole. There are some caveats there, which you actually compute as an index, but it pretty much holds together. And then there were a variety of near extremal extensions. And finally, the ADS CFT correspondence, everything seems to hang together. The black hole area is matches nicely to the thermal entropy of the dual. The Hawking temperature is just the temperature of the dual field theory. So things look, the dual is just some quantum field theory. So it seems like there should, all consistent with their statistical origin. So you might ask if there's a more direct gravitational interpretation, one that you can just sort of talk about directly in the, if you like, in the bulk. And so there's the fuzzball program has been quite successful in accounting for the entropy for BPS black holes, and there's a lot of progress for non-BPS black holes. So that's one. You can also try to understand the black hole entropy as an entanglement entropy. Now, this is not quite using gravity. You could look, for example, at the entanglement entropy for fields propagating up the horizon. And when you compute this entanglement entropy, there's a divergent contribution. But that divergent contribution can be precisely absorbed by renormalizing Newton's constant. So you're left with, when I include this divergence and I properly take into account the renormalization of Newton's constant, it's consistent with the entropy still being A over 4G Newton. So you might think this is this black hole entropy is some sort of entanglement entropy. You still have to understand the tree level result, and that's open. There was a nice, a very tantalizing suggestion in the early 90s by Susskind and Nuglin. You also might wonder what the relation is to the state counting programs, which have been very successful. So I'm not going to address any of these. What I'm going to do is argue that at strong coupling, we can at least we can use supergravity to come up with an argument that this is the right, not supergravity, sorry. I'm old enough that supergravity often just meant low energy gravity, and that's what I mean. We're going to use low energy gravity, no supersymmetry here, to argue that this all consistently hangs together. There are signs in supergravity that this is true, or in low energy gravity, semiclassical gravity, that this is true. And that should be consistent with, certainly consistent with these, and we can talk about whether it's consistent with this. I suspect it might be. The second newer puzzle we were interested, that sort of got us going on this, is a conjectured relation between the complexity of a state in, so in ADS-CFT. If I look at, say, one of these two-sided black holes, this is dual to a product of two conformal field theories in a highly entangled state. That state can evolve with time, or you can evolve, although the sort of standard time evolution involves slices which go like this, you can choose a different Hamiltonian which evolves like that. And by that Hamiltonian, there's an Einstein-Rosen bridge connecting the horizon, which grows in time. And Susskind suggested that that was going to be related to the some complexity of the corresponding state, the amount of gates you would need to prepare this state from some reference state. Or if you like, the number of gates needed to construct the time evolution operator going forward. I just stole this picture from Standard Susskind. Now there's an issue here that, so there's a lot of definitions and variants of both sides of this equation. But in general, the issue is that if I compute some sensible notion of the complexity of a state or the complexity of time evolution, this complexity saturates at a time scale, according to some units, of the order of the dimension of the Hilbert space. And then there should be, later on, we won't deal with this so much, there should be things like Poincare recurrences where you'll get dips in the complexity of order e to the image. Now, the problem here is it looks like the volume of the Einstein-Rosen bridge can grow without bound if you go this way. And then it's an open question how that's consistent with this saturation here, where the dimension of H will be e to the s black hole. So, like I said, it's we're sort of dealing with a conjecture that's a little bit squirrely on both sides, but this behavior is fairly generic. So we'll sort of take it as something that puzzles us and that we should watch out for. So what we propose, I don't know, the solution to both or an explanation of both within semiclassical gravity. Perhaps a sharper way to say that is with sort of semiclassical gravity contains within it information that indeed the dimension is finite. It's e to the s black hole, and that the complexity volume ratio will saturate in some way, precisely where it should. So we're going to focus on two-sided or eternal black holes in ADS. We'll discuss one-sided or asymptotically flat cases if I get to the end and people don't ask enough questions. And we're going to, I don't think anything we say depends on ADS-CFT, but it gives at least me a useful conceptual approach in talking about these things. We'll construct a family of black hole geometries with different shells of dust in the interior that we'll treat in the thin wall limit. So certainly this is an area where you could complain about the construction. Is this actually consistent with the, but assuming that we can do this and we can actually treat these in the thin wall limit, things hang together. These have Einstein-Rosen bridges of arbitrarily large volume already at t equals 0. So it's not just an issue of these things growing with time. I can make these bridges large to begin with, and that already is confusing with respect to the complexity equals volume scenario. We'll use an explanation of semiclassical wormholes by Twosided, arguing that the average over some sort of ensemble that's suggested by the Eigenstate thermalization hypothesis to demonstrate that different, apparently rather different interior states have small but finite overlaps, and we can estimate the size of this overlap. And then we'll argue that this implies that only these many states, these interior states, are linearly independent of each other. This seems to lead, at least suggest, that the complexity volume conjecture needs refinement, as I'll argue, because long wormholes are linear combinations of short ones, and maybe it will give us some other ways of thinking about black hole interiors. So I'll say from the outset, there's a lot of holes here, and a number of approximations we make, but we get an answer which is very plausible, and I don't think we've made any circular assumptions. So that at least suggests that there's a lot to think, that this is, what we've done is we're thinking about hardware plugging in the details, pushing the implications and so on.
And how essential to the line of reasoning are two-sided black holes? Can you, are there analogous construction for single sided?
Yeah, and we'll talk about that a bit at the end. Yeah, you can do this for one-sided black holes, both in ADS or asymptotically. I'll construct them at the end. I'll describe the asymptotically flat one-sided geometries. No, it's just sort of easier when we started to think about it. It's really a crunch. Okay. So I'll just launch in and first talk about what these geometries look like. So first, let's talk about these geometries in Lorentzian space. We can also talk about black holes which form from collapse at the end. We'll talk about right now eternal black holes, things that look like eternal black holes. We'll build our geometry with shells of dust in the thin shell limit, which means amounts to joining different ADS black hole metrics together across some shell using Israel junction conditions. We'll have black holes with some fixed mass and therefore some fixed temperature on each side. These could differ between the two sides. And put shell masses in between. Now note that these shell masses can be much, much bigger than the ADM masses on each side. The shell mass is characterizing the local stress tensor, but the ADM mass is a global quantity. And so the details of the geometry will depend on M in such a way that this is all completely consistent with the point of the junction conditions. So here's an example of a single shell geometry in d dimensions with the ADS radius the same on both sides. I have some shell of dust behind the horizon of both black holes. And I glue them together in some particular way. And so these lines, so this is the exterior of one black hole. This would be the interior and the other exterior, but then you glue it on to this other black hole here. So these two exteriors sort of sit in the middle, and then I have these past and future singularities like so. So here I'm going to be talking about spherically symmetric shell geometries. Somehow get the answer right. Of course, this should be consistent with the fact that these should have overlap of non-spherically symmetric configurations that I would expect would be part of the entropy of the black hole. That's something we need to chase now. To mind here, we're going to be looking at global Lorentzian ADS. So this has an asymptotic boundary, which is SD minus 2 times R. This is all ADS-D, where D is the space-time dimension. Good. So let's just look at here. I'm just going to look at a slice and t equals 0. So here is the SD minus 2. And we'll go out this direction are the two asymptotically ADS directions. I have a horizon. This is the location of the horizon from the point of view of the right, the horizon from the point of view of the left. And then I have a shell in between and an Einstein-Rosen bridge. And if you measure the volume of this spatial slice between these two, and compute this, you get a volume which grows with the mass of the shell. And in the complexity equals volume scenario, this combination is taken to be supposed to be somehow the complexity of the state that you prepare as to get the state from some reference maximally entangled state.
This is the volume on the surface of time symmetry.
Yeah, that's right. And the point is, for here, we can make this arbitrarily large already at t=0, so it's not just an issue of time. By the way, this is a sort of standard example of a Python slunch geometry where, depending on the relative size of these, the smallest, this would also somehow be related to some complexity here. And then one would be the coarse grained entropy in the fine grain. I'll just mention that, and then the area of the bulge also is the same as this with a factor of 5. We can also do this with multiple shells. Again, it's just gluing together pieces of the ADS black hole geometry. This in the middle, these would be exteriors, interiors here, and so forth. So they're just different ADS black holes. We again fix the temperature and the mass on each side. When you look at this slice, there is going to be a couple bulges in these constrictions here. And so again, we can make this length arbitrarily large at t=0 by adding more and more shells, as well as by cranking up the mass of one shell. Next, and this will actually be important for our calculation, we can prepare these using in Euclidean space, and this gives us go into a little bit of detail here. So we're going to start with two different black holes, Euclidean black holes with some set temperatures and therefore dual masses. We are going to glue them together with a shell like so, and in this shell, this carves out. We're going to carve out a piece of just throw away these little dotted pieces of the geometry and glue them together. The remaining pieces of the circumference I call beta tilde right and beta tilde left. And they're going to be related to the actual temperature by the sort of missing bit of the circumference. So I get some Euclidean geometry like that. Again, this is the horizon. This would be the boundary of one black hole, the boundary of the other black hole. These are the horizons. And now I can take these and, for example, prepare semiclassical Lorentzian states by taking this point of time, Euclidean and Lorentzian time reflection symmetry, and gluing on the t greater than 0 Lorentzian solution to the Euclidean time to this half of the Euclidean geometry. The shell continues to Minkowski space. These green dots, which correspond to the horizon, then glue on to these points here, and then things evolve forward. And here, this is all about, this is a Euclidean boundary of Euclidean, if you like, of Euclidean asymptotically Euclidean ADS, with some insertion here of stress energy. I will have a Euclidean distance for these beta tildes, and then they match on to these actual betas here through this one. We're guaranteeing, we're essentially, the upshot is going to be that given some amount of stress energy, which we fix and is related to the black hole mass, we will propagate the, we will sort of move by beta tilde r in this direction, beta tilde left in this direction. These are going to be fixed precisely so they match on to the right.
So there's some assumption here, maybe it's related to large N or something, that this, so if I was asking what is analogous to that geometry in N=4 Yang-Mills, I think I would say that I have some boundary operator that's making some kind of domain wall.
This picture, which one?
Okay.
Let me,
I guess my question is, why does it remain localized in the bulk? I mean, it's just a generic boundary operator would stick in that point, which spread out.
So we're going to assume that there's, really what I'm going to say is we're going to assume there is the shell in the bulk, and we're going to continue to the boundary and assume there's some reasonable operator that compares it.
Do you have an idea of what sort of thing in N=4 Yang-Mills would have those properties?
To be honest, no, we're assuming the same. This is one of those areas where there's there's work to do. So we're assuming that this thing makes sense, that I write down some, this will probably be some product of single trace operators corresponding to some shell of dust. Assuming we're going to assume that the shell exists. This is an area, like I said, there's an assumption here. I'll completely own up to it. It hangs together, but one should poke more. Absolutely. Good. Okay, so I think I've said everything to see here, so I'll go here. So this is the boundary interpretation then. I'm going to insert some, so here, again, remember I'm going to start with this little cylinder here. Remember what I call the circle direction is actually going to be the SD minus 2. And we're going to continue it on each side by some amount, half beta tilde r, half beta tilde left. And then at this point, just glue things on. Actually, I think the factor of a half is a mistake. No, that's right. And then I'm just going to glue it on here. Yeah, no, the factor of a half is correct. And then at these points, I will glue on cylinders so that this prepares a state in the tensor product of these two conformal field theories on the sphere. And the state should look something like this. There will be some matrix elements of this operator between, you can think of this as a ONM, or the matrix elements between energy eigenstates, and then we propagate this way, and that propagation weights gives us these weights here. Again, we expect these are single trace operators with some dimension delta, dual to some bulk field. The mass will be the total number here times the dimension of that operator. We don't worry too much about that. We actually get something rightfully complain about. So these shell states are states in the dual CFT2, and these are some sort of microstate. What we get are some sort of microstates geometries of this two-sided black hole. At least some rough approximation of them is proven. Microstate is a little stronger. Okay, so that's what we've got. And so now, given this, I want to ask about how these states relate to each other. And I want to argue that even though these states look very different, so Euclidean semiclassical gravity seems to be telling us that there is a very small but not trivial overlap between these states. But there are so many of these states that we can actually estimate a bound on the dimension of the Hilbert space of the black hole. So that's what I want to sketch out next. Are there any questions? Other questions so far? Okay, so I'm going to rely on an interpretation that at least I learned from my postdoc. So basically what we both happen to be down at Penn at the same time, giving talks to two different groups. And, the conversation that led to these papers immediately followed. So let me go back and talk a bit about, just briefly sketch the eigenstate thermalization hypothesis as developed by Schrodnicki and Deutsch. So there's a class of operators, so the goal of the eigenstate thermalization hypothesis is to explain why sort of the microcanonical ensemble made sense in quantum mechanics, because a state of definite energy doesn't evolve. So it's sort of, you have to understand how you would get sort of ergodic parallel averaging. And the argument was that if I look at the right operators which sort of behave thermally, and these are some people call them simple operators, have the structure, the matrix elements in the energy basis will have a diagonal piece, which will be a function of the mean energy. And then an additional piece, which is suppressed by e to the minus. So roughly speaking, S of B is the entropy, would count the density of states at that given energy. I'll get some smooth function of the average energy between M and N and the energy difference. And then a matrix here, which is random and has which is effectively random and has variance 1. So,
and the e to the minus s over 2 is
this this gives sort of good sort of expected corrections to expectation values of the operators and the 2-point functions of the operators. You make this assumption, and these things behave as they should. So we're looking at theories with ADS duals, and we haven't given you. I haven't given you a lot of information about the details of that theory. And I'm going to be doing these calculations in semiclassical gravity. And I, at least, expect semiclassical gravity to be rather insensitive by itself, to be insensitive to the UV details. There's lots of different, there are a number, if I'm just looking at ADS and with some definite ADS curvature and gravity, and just some vague stuff about shells of dust. I expect there's a lot of different UV completions of that theory, which just any semiclassical gravity calculation by itself will be invisible. So, and I expect that in particular that these random matrix elements, the detailed values of these random matrix elements are really require knowing the precise details of the dual field theory and therefore the precise details of the bulk theory because they're dual to each other. So then depend on the full UV field theory. So the conjecture is that if I try to do calculations of correlation functions or of moments of products of correlation functions in supergravity, including some effects, I'm effectively averaging over some random ensemble from which I draw these RMNs. These will be random matrices of variance 1. And the claim is that these averages are captured by semiclassical gravity. And there's a lot, I admit, I don't understand here, but what Martin showed was that that making this assumption gives you plausible answers. Because making this assumption, we can compute moments of correlation functions like this using Euclidean wormhole technique, which I'll describe in a bit, and got answers which are consistent with ETH. So that's what I'm going to do. That's what we're going to assume here. You should certainly bug me about this one. So in particular, let's look at variances of correlators. So the argument is I can compute some average, say average over the CTH ensemble. I claim this is captured by supergravity. This average will involve the original 2-point functions calculated by a standard ADS CFT. Here's the 2-point. So there's a product of 2-point functions. Here's one 2-point function. Here's the other 2-point function. This brown hash region is the bulk. This is the boundary. I've inserted some operators here, some operators here. And then I get a sort of connected piece because I'm treating these 2-point functions in some sense as random variables with some moment. I compute them with ETH. And the argument is the moments are captured by these wormhole techniques. And that was Martin's suggestion. This is related to these, for example, discussion by Saad Schenker and Stanford in 2 dimensions. Argued that 2-dimensional gravity was captured in some sense by random matrix theory. I'm not making any claim that the underlying theory is statistical or stochastic or random in any sense. I'm just saying that when I do these computations, at least for operators connecting high enough energy states, that semiclassical gravity is somehow averaging, it's giving you a sort of sensible average. It's consistent with pretending that these matrix elements are random. So, and that's certainly what Martina argued, that if I assume that this, if I compute the action of this wormhole, it's consistent with, I get answers that's consistent with what I would expect from this from ETH.
And what do you have to say about the factorization confusions that dog other uses of this statement?
Nothing yet. I'm just going to claim this hangs together. Talk about that in this content. I'm not making any assumption that these should, in principle, if you do a calculation in the correct theory, fix a UV theory, compute this 2-point function. There's no averaging involved. So this is just something about, if I'm doing semiclassical gravity calculations, these wormholes that are encoding some information, if you like, about the strength of the variance of these correlators across different theories consistent with VRR, with the semiclassical gravity.
But I guess my question, you're after something that's exponentially small.
Yeah.
And so how do you know that your exponentially small thing is due to what you're interested in rather than some noise or error that you're making by doing the computation in semiclassical gravity?
I would have said this is that noise or error. It is measuring that noise or error. Okay, so there is there is one question we'll get to. Maybe that's the same. Let me go on. So there is one issue, which maybe is what you're saying, which I'll get to in a minute. Because I could, as you say, just in the calculations I'll do there, where we're looking at overlap between these states, there is some potential. I think it'll be easier to table that and I'll come back.
All right, I'll ask.
Table it and come back. Yeah, that's a fair question. I think it answers it. So we're going to look at a particular family of microstates for two-sided black holes with fixed asymptotic, the same asymptotic temperature on both sides. There's an apparently infinite number of shell states. We want to know if they're linearly independent. We're going to show that. So in general, I can just have multi-shell states of arbitrary mass. We're going to consider a specific family of single shell states generated by shells of already some initially fairly large mass. Now, the masses will be, T is something we dial, N is something we fix, which is of order big M squared, where N is the central charge of the dual field theory. And delta is going to be some mass of order the ADL scale, corresponding to operators of small dimensions. Shells of large shells of dust. And so, this is where you can tell me where this is related to what you're thinking. So we want to compute overlaps of dust with different shell masses. And I want to compute the overlap, say, between MP and MQ. And you might, it is certainly true that already, if I really was to be careful about what these dust shells come from, there will be some small, there will be some highly suppressed interactions which transform these shells of dust into each other through particle annihilation and decay. But we expect that those effects will give us something which is exponential, the difference between the shell mass, which will be subleading to the world contributions for large shell mass. So I don't know if this is what you were thinking of, but this is suddenly one issue that comes up. So this is already a sort of an error in not taking the quantum fields in curved spacing.
So you want the shells to be enormously more massive than the black hole you're.
Yeah, that's okay.
Why is that okay?
I mean, the first answer is you can look at, it's consistent with these real junction conditions. It works because I have these long wormhole geometries that ensure that the ADM mass I measure on each end is less than that shell mass, which is all sitting inside the interior.
But you're sort of asking that you have some past singularity that magically nucleates some domain wall, which is enormously more massive than the black hole it's emerging from.
Well, it never goes out of this. If you look,
It's behind the horizon, so you can draw anything you want. It's this typical bag of gold problem.
Right.
But it sounds like you're asking to draw out of the bag of gold.
I'm assuming that
Jupiter.
yes. I'm assuming that this is reason, and it's it will have small overlap indeed with just vacuum black hole. Extremely small overlap. Not a highly probable process, but it's there. It's a state. That's no, I agree. It's a little bit weird, but I think it's consistent. Again, like I said, this is going to be something which would.
I guess my confusion is, why isn't this like arguing about some even more remote tail of the wave function than what you would expect to be some kind of generic internal state?
I don't know if this answers your question, but we will compute the overlap of this with other states. Which, if I ask, how does this state relate to some other state, or just a single shell state, which relate to some state with a massively different shell? It's a similar kind of question. Why would these two be related to each other? How can I go from one to the other? What's the overlap between these two states? That kind of gets at this question. And so there is a very small overlap, which is estimated by semiclassical gravity. It's insanely small, but there are so many of them that when we compute the matrix of inner products, we'll get a bound up.
I guess my question is the calculation you're doing only reliable in this limit where little m is much bigger than big M, or how far can you push it down into the regime of, like, if I was interested in actual states of Hawking quanta on some nice slides, right, where my little excitations are tiny in energy relative to the mass of the black hole.
I think at this level, what we're doing is not going to capture that.
Okay.
That's fair. You would have to think if these masses were small and I started getting more order one overlaps here. The overlaps would be larger, and so therefore, I would also say that if these overlaps were of some size, or for shell masses that are close to each other, I'm not sure it contradicts what we're saying. What we're saying is there's a large family of states which seem to have very little overlap. Semiclassical gravity argues there's some finite overlap. It's very small but finite overlap, which can sort of build on. A lot of these things.
I guess what I'm confused about is why isn't this computing like overlaps of things that are like way out on the tail of the wave function?
I think they're out on the tail of the wave. They're different states of the. They're sort of different states in this ensemble of black holes of some mass. And
Right,
so
I
I'm not
guess-
sure what you mean by tail. Of the
Well,
wave.
so right, so you if these are states that have shells that are hugely massive, I guess I would have thought that their overlap with each other, how to say this,
It's small.
is small. I guess why, how is it that you're able to account for things, the correct calculation of the overlap of things that are less unlikely?
I somehow, the answer is that somehow, at least, so what we're arguing is that, so there would be a leading order term. The leading order term is extremely small. So the first order correction is somehow the first thing. Again, we're arguing that these Euclidean wormhole calculations and this limit give you a reasonable estimation of the sort of leading estimation of the overlap is consistent. So we'll just start, and it will hang together somewhat. So I think I would say it's, yes, you should worry about it, but it's sort of like, I've got first order term is small, the next order term is somehow estimated reliably.
Okay, well, keep going.
We can keep talking, absolutely. That's great. You can also compute higher moments just by gluing together. So here's a piece of these are the boundaries, these colored lines are different shells, we glue them together. And for sufficiently large masses in general, for nth moments like this, we sort of universally get a ratio, which is z to the n beta, where beta is the temperature of the black hole we started with, and n is the number of the moment, divided by z beta to the 2. Small number, but it sort of comes out. So given this, we'll try to get at the dimension of the Hilbert space. So we have this large family of states. And these states generically, we're arguing, what semiclassical gravity tells us is they generically have overlaps of, and those overlaps were which are, the generic size is estimated by these wormholes to be this ratio for single cell states. And so now we want to know the number of independent shut states, and that will be the rank of this matrix of inner products. Yeah.
Yeah, I've got a question related to Anil's last question. Is that maybe not understanding this fully, but it seems what I'm not understanding is that these sort of geometries that you construct that have such massive shells in the interior, you're kind of saying that they're somewhat like typical states. They capture.
I'm saying there's a lot of these different states. No, I'm not saying that one of these shells is when you're going to. There's a question of what happens if you form the thing from collapse. If that's what you know. I'm just saying that there are this large family of states. They're there, and they have small overlaps, and I can get an estimate of the number of independent substates.
So I guess that what I'm not fully understanding is the fact that those states with these such massive shells are kind of typical in some sense, because you're kind of working with those to kind of learn about the microphysics of these black holes, right? So
The rather large states of the rather large number of states of the black hole. I think right now I'm just going to argue that these states seem to be there. They have this overlap. I can compute. There will be many other states as well, but they should, if I've correctly constructed a basis, they should somehow be. I should somehow be able to write them down in this space, the basis that I constructed. Crazy coefficients.
Maybe the style of reasoning is that is that there's sort of a minimum size bag of gold that you need to realize this exponential complexity, but you're saying, I don't care that I can look at an exponentially bigger bag of gold that has even exponentially rarer states in it and use those exponentially rarer states as a basis for,
Yeah.
okay. What's going on?
Yeah.
Okay.
No, that's a very good question. So, I mean, like I said, I'm arguing here, I've got a bunch of things, I think I've got a bunch of approximations, it hangs together, but it suggests a lot of questions. So the calculation we do is essentially just importing a paper by Pennington, Schenker, Stanford, and Yang, remembering the authors correctly. So we're going to start by computing the resolvent of the Grand matrix here. We're going to, so the resolvent which is this, I'll argue that the density of states can be related to looking at this resolvent around the behavior near a cut. This resolvent will have, a branch cut, and the behavior across this cut will give us the density of states. So first, let's compute this. I will take both sides and I'll ask what is their average in this mysterious ETH ensemble, and I'll say this average is sensibly computed in semiclassical gravity. So I'll get these nth moments, which I compute by wormholes. And in the limit that the wormhole action is reasonably small and the dimension of G, the Grand matrix, is large, which we expect it will be consistently, I can resum these to get this answer for the resolvent with these coefficients, which are related to sort of the connected pieces of these. To actually solve this for the resolvent, it is easier to pass to the microcanonical ensemble, which means I have to sort of project. So the states I've constructed so far aren't energy eigenstates of the full theory. I have to somehow project them into a microcanonical energy band. So if I look at the Grand matrix between two states, I can look at the contribution from different microcanonical energy bands. I'm assuming these overlaps are statistically independent for different microcanonical energy bands. And the connected moments are non-vanishing only if the connected moments like this are non-vanishing only if all of these G's under the bar are in the same microcanonical energy band. So I can go back and compute this resolvent in the dimension of the Grand matrix restricted to a microcanonical energy band. This is, by the way, the same assumption that PS and Pennington et al. Use with somewhat even more telegraphically than I've done. And so in doing so, finally I can compute this, and I'm going to argue that the projection of this answer onto the energy band, well, I can write Z and beta in terms of Laplace transform. So I'm just going to undo this Laplace transform here. I can compute this directly, and I end up getting this. This collapses to this sum, and I take the trace of both sides. And now this is an equation I can actually solve. Where here, what we will find is that S of B is in fact the black hole entropy for the two-sided black hole, which I got by inverting this Laplace transform. So now the density of eigenvalues of the Grand matrix is the difference of the resolvents across the cut. And I'll get this continuous piece here, and I'll get a delta function here, which counts 0 eigenvalues, and there will be none if the size of the Grand matrix is larger than E to the S, where S is the entropy of the two-sided black hole. So I have E to the S independent states, this projected basis. So that's a statement that when I make all this set of assumptions, I naturally get out a set of independent states, the number of which is equal to E to the S, where S is the Hawking-Bekenstein entropy at this leading order. Finally, just a few statements about these large volume wormholes. So this is the general basis. There is this complexity equals volume conjecture, where the complexity is related to the volume of the Einstein-Rosen bridge, which scales as the mass. Very large volume wormholes seem to exist. These are, the shell masses would be very high, or I could have lots and lots and lots of shells. But we expect that if the volume operator is linear, it should be bounded by the large volume of the largest wormhole in this basis. That should somehow saturate the definition of this volume operator. So what it does suggest is that part of the resolution of this confusion with the complexity equals volume operator is that truly that in some sense the volume operator as an operator should be the maximum, the there should be sort of a maximum volume in terms of being there's a maximum eigenvalue to the of this linear volume operator. And finally, it's what it's reminding me, and the point underlying this is that if I correctly accounted for the spaces, these very, very large wormholes, I can construct a linear combinations of shorter. Okay. Any other questions? So I'll just finish up then, because I have a little time, and just sketch out the story with asymptotically flat one-sided black holes. Here again, we're going to take the eternal Schwarzschild black hole here, and we're going to consider join it to this little sliver of flat space with some shell here. So this example here involves a little shell here and then some flat space cap. And in the exterior, this is a t equals 0 slice. And now we will extend this. I can also write down different shell masses where the shell would have gone into the other region, the second region of this two-sided black hole, but then gets capped off here with a little piece of flat space. And these are the sort of bag of gold states for the Schwarzschild geometry. Here's a big region back here, supported with the shell mass. Here's the horizon, here's the exterior. And similar, so I can once again compute the overlap between different states and get the same story as before. I'll get here is the Euclidean metric we're talking about. So you can think of the Lorentzian metric as sort of sticking out in real time. This is imaginary. This direction here is imaginary time, and this upward direction is real time. I can construct various wormholes between these. So I have a piece of flat space black hole joined across shells. These are the horizons. And the story ends up being, and the calculation ends up being the same. So finally, just as I've been talking about these two-sided eternal black holes to account for the entropy of all the possible states that are consistent with the exterior geometry. What you actually find in the real world, of course, is that I've formed future shells from collapse, and the past is somewhat simpler. What I think the right way to think about this is that when we say that we're counting entropy of some set of states, we need to compute states, the entropy of states along some slice, some nice slice or other, long after equilibration. This system is equilibrated. The entropy is going to be the log of the number of all states consistent with the macroscopic exterior geometry at late time after its equilibrium. This will include interior perturbations of the shell, which are past singular. And I think this is a bit like looking at a gas in a box. Most microstates contributing to the entropy of the glass in the box will have past very different from the actual history, which is typically an initial state with full entropy. All sorts of crazy, and the there are crazy histories in the if I extrapolate to sort of your generic configuration of gas molecules in the box. It's sort of related to Lenny's complaint that if you think of the thinner space as a closed system, many small perturbations of the present will give you something that doesn't make sense. Volkswagens fossilized at the same time as dinosaurs. This is a more prosaic explanation, statement of the same. So that's what I have to say. I finished a little early, which I apologize. But so again, I'm assuming that I can use these Euclidean shell states to prepare states of the black hole, that there are they reasonably capture some microstates of the black hole. I'm looking at two-sided ADS black holes so that I can sort of lean on the ADS CFT correspondence to think of these things as really states in some theory and some underlying theory. I'm assuming that semiclassical gravity is insensitive to things like the phases of a given sort of phase factors that put in front of a given state, the UV completions of the state, and so forth, and naturally compute average over this ETH ensemble. That wormholes compute moments of correlators, wave functions, and moments of overlaps of states. The characteristic size of the overlaps are naturally computed from these wormholes, and because they bound the log dimension of the black hole Hilbert space, the black hole entropy, to be the Hawking-Bekenstein entropy at the order to which we work. There will be corrections, of course, famously, from theory. effect, which, you know, which should enhance this, should change this to the low entropy. And finally, that exponentially large wormholes are linear superpositions of short wormholes, and at least this, to me, suggests one should go back and think hard about what's going on in the interior, about my slices and so forth, though I don't have any grand ideas yet. So something going on here. I think this is consistent with, to the degree I understand it, with these statements of non-isometric embeddings by Harlow. And I will just end with that.
Let's thank the speaker.
Can you restate your comment about de Sitter space, concern about de Sitter space?
Oh, no, I was just remembering, so one of Susskind's complaints about the existence of eternal de Sitter space was that these things do have a finite entropy. And so it was sort of hard to understand in general why you might think that you start from some low entropy initial state. If you take the universe as observed today, you can make very small changes that are almost unrecognizable, and the past would be almost invisible, and the past would look totally different. So that was just a complaint, because he was going to say, why can we, given what we know about de Sitter space, the existence of Poincare recurrence and stuff, why is it all natural to assume that we can start with some low entropy initial state? When you usually think about cosmology, it makes standard cosmology seem a little less likely. So I won't wade into that debate, but I say underlying that is the statement that, like, if I look at a box of gas, typically I prepare it through some process that might have fairly low entropy, box of gas with some temperature and some pressure and so forth. Gas molecules is doing everything that's always prepared, typically some low entropy initial state. Inject gas into a box and the gas expands and so forth. I would compute the entropy by looking at all possible states of that gas. Most states in that ensemble would have very weird initial conditions. So so the states I'm saying, the states that's why I think I can reasonably account for the states using these eternal black holes, but the states you actually form from collapse with these very weird linear things. So there's something I haven't gotten my head around. I was like, how do I think about it? But at least it's not insane that the states that form from collapse will be a small subset of the possible the states that count the entropy.
So I guess I'm still confused about this question. I keep on asking in different ways. You're somehow getting a handle on the Hilbert space by looking at extremely unlikely configurations.
They're unlikely from the point of view of an eternal. I guess I don't know what you mean by unlikely. They're unlikely from the point of view of, say, just the eternal black hole with no shell, in the sense that their overlap is small. But which is kind of the point. But I can just prepare these as a state. I mean, I know what you mean by unlikely.
Well, unlikely in the sense that that I have some past singularity, and I'm asking that some collection of extremely massive shells somehow, emerge from the singularity and then disappear into a future singularity.
So again, I think is what I'm saying. I can prepare that state as long as what I've done is consistent with truly consistent with microscopic radius COT. I could just prepare a state where this shell is emerging. Okay. And then what do you mean? And then it's just the state. There's no unlikely about it.
Right, but there's sort of like exponentially more likely things to emerge from the past singularity that I would have thought I should look at first.
But then I asked, what do you mean? I mean, there are different states. There's the past singularity with nothing emerging. There's the past singularity with something emerging. There's past five shell emerging. Each of those are different states to put in the past.
Right.
And I can just choose one of those states. It's consistent with the asymptotic geometry. So what you mean by unlikely, I think, is exactly what is the overlap between that and, say, the black hole with no shell. Right. And that will be small.
Right, so I guess it's sort of a surprise to me that you could sort of capture everything in terms of linear independence by looking at just these extremely unlikely.
I'm making sure that the overlap between every single state is small. And so that the lowest order, in such a way that the lowest order, there's going to be a sort of non-wormhole piece, leading order in the supergravity, apparently leading order in the supergravity approximation. So made sure that the overlap at this order is small. The leading correction is this semiclassical, is computed by this semiclassical spacetime. And this dominates, this captures the overlap. So I have to make sure that the, if I was to choose some other set of states, which had more overlap, they would have more overlap. So it would, they would saturate out sooner. I probably wouldn't get everything. And then of course, these would be subleading. So I have to be careful. I do have to be careful to make sure that this is the leading order. I've chosen a set of states. This is leading. This is the leading order correction. For this to hang, for this story to hang. So it sort of gets at, I mean, when we look at the black hole, there's this huge family of states which are massively overcomplete. It seems like it's completely inconsistent with the finite entropy. If I just pick members of those which have very little overlap, so it looks like there's really a problem. I go back and compute their overlap, it's small but finite. And there are enough of them that I build up.
Can you use this sort of analysis to say something about dynamics in the following sense? So it sounds like you're saying that if I had, some collection of stuff that's sitting on some nice slice, having fallen into the black hole, that there is some it has exponentially overlapped with all these things that look crazily different.
Yeah.
And all those crazily different things have different evolutions.
Right.
And so I guess what I'm asking about is maybe some kind of coherence time for, if I put a blob of something on some slice, I could ask sort of like, what is its coherence time, that where I can actually identify it as something that's reliably
distinct from everything else.
That's distinct from everything else. And I could worry that if it's really has an overlap with all sorts of crazily different things, that if I wait a little bit, it just sort of completely disappears. It's sort of this idea that the black hole interior is some kind of chaotic mess.
Yeah.
And so I would expect that if I have something that looks like it's naively some coherent thing, that it's going to fall apart in some kind of, coherence time. And I don't know if that's different from the time it takes for the thing to hit the future singularity or not.
Yeah, that's, I'll just say that's exactly the kind of question I want to start asking. My first question would be, does it happen before the singularity? Sort of tried to get handles on, let me say, questions of, can I see, for example, the saturations, the thing gets big in terms as some question about what families of observers can see, how much of the interior can different families of observers see. So can some interior, so if I have some interior observer, let's say naturally, appears inside the black hole and trucks along forward is measuring things, how much of the interior can it see? Is that somehow saturated? Not gotten a sensible answer for that.
So your massive shells, so there's some characteristic time in the vacuum geometry, which is basically, there's no other scale in the problem other than the mass of the black hole, which is sort of like the time it takes to go from the past singularity to the future singularity along some time like path.
Yeah, let's go.
So your shells, when I make them much bigger than the black hole, the sort of persistence time of the interior is much shorter than that scale?
It could be, because this is the thing about this is the exterior, this region is the exterior of the dimension of the black hole exterior. So.
I guess the question is, if I, as I make the black hole, as I make the wormhole longer and
Right.
longer, is its persistence in the time direction?
Yeah,
shorter?
I think, well, here, like, just to see, so if this is the wormhole here. Somehow, somewhere around here is where I would start to. See the exterior, and then this is. Less than an ADS time. Less than the time scale of the black hole. I need to sit down and think about it. Very quick on this. But that, no, this is. the right question. I was hoping for some sort of causal patch like argument. That this truncation is somehow sensitive.
Let's thank Albion again and. Continue the discussion.
Thanks.